Hello, it's Keith here, and this is lesson 11 of the platform-specific series of my Z80 programming tutorials. Now, as promised, we're going to have a look at this week about how to create a tilemap style effect on the MSX2, because as I said before, the MSX2 isn't actually a tilemap-based system, but it works quite nicely if we emulate one on it. So you can see the example we're showing today here. It's the exact same source code as we compiled onto the MSX1 and the Game Boy and all the other systems before. The hello world message, the Chibiako sprite. As usual, the Chibiako sprite is compiled for this specific platform, and as usual, my sprite editor can export in the format that we need for today's lesson. So we're going to be looking at how to create the tilemap, but that actually extends to something much more significant. This is the first time we're really going to look at how to use the VDP of the MSX2 as it's really designed, and that's as a block copying piece of hardware, because last time we were using it to access the memory directly. It's very slow and inefficient in that form. What it's much better at is working in box areas and performing tasks on those, like copying one area to another, and even filling an area, in today's example 8x8, with bytes that we pass via out commands, which even in that sort of relatively crude example is still far more efficient than doing the same thing by repeatedly relocating the address pointer every time we want to start a new line. So we're going to go over the commands in the lesson, and as usual it's on my website here, but I've also created a general page on the MSX2 on my website now, which goes into quite a lot of detail about the MSX2 in general, because to be honest, the details of the MSX2 VDP are quite substantial, and I didn't want to ignore bits that were too difficult to cover today. I wanted to have everything there so I wasn't deceiving you about how much was there, but we aren't actually going to need it all today. So the MSX2 VDP has a set of registers. These are controlled by out commands. We set those registers to certain values, and then those values combine together into a command. The command uses those values and performs the action we asked. So for example, if we were going to copy the top left corner of the screen to the bottom right corner of the screen, for example, we would give it the coordinates of the top left of the screen, the width and height of the area we were copying, the destination location, a few other special commands which we'll look at as well, and then the command to actually start the job. And we have to put all of those into the correct register locations in the VDP's memory. We then have to send a command, and these are the commands that are available. And we also have to check status registers to see if the last job we finished was done, because unlike when we're working with a simple system like the Amstrad CPC, where we tell it to do a command and we're kind of stuck doing that command, with the MSX2 VDP, the processor is actually doing the work and we don't have to do anything, so we can start doing other jobs. So we can work out where our enemy is going to be, calculate if it's been shot, draw it, start calculating the next enemy, and the VDP will actually still be drawing the sprite of the last enemy while we're doing the next calculations. So the benefit is we can kind of do two jobs at once. The disadvantage is we can't start drawing that next enemy until we've checked that the last one really finished, because depending on the sprite size, there's every chance it won't have, and if we try and start drawing the next one, the last one will only have a bit of drawn and you might get odd effects. So we do have to check the status registers for that. We have to know our commands for the commands we're going to do, and we have to know at least the registers we're going to use, and that's basically register 32, start X, down to destination X, and then number X, which is the width and height. We then have a color command, which we do have to use in some cases, a direction command, which it's called arg bank switching, but effectively it programs whether we're starting left to the right or bottom to top, that kind of thing. We always, in my code, go left, right, top to bottom, but if you're doing a scrolling routine where you're copying the screen over itself, you might want to work the other way around, because there's no buffer. So if you're copying the screen over itself, you have to write in the right direction, or all the pixels will end up the same color. And then the most important one is register 46, which is the actual command, and we have to send it one of these commands, and you can see the bytecode in this column here. Now this is all very confusing, and you're probably already screaming going, oh my god, I can't be bothered to work out 46 registers, I can't understand all of this. Or, well, don't worry, because what we're actually going to use today is the code that I've taken from my ChibiAkumas game, and this does most of the work for us. All that we do with my code is we give it a simple array of data. We say we call a command, which is the name of the action we want to call, and it does it all for us. And one of the big benefits of this is the one we're going to look at today is for the MSX2 VDP, but there is an identical function for the V9990, the V9K, which will do the exact same job with the exact same parameters. And so if you use my functions that we're going to look at today, you've immediately supported the V9K as a bonus. So I think that's going to be quite interesting. So as you can see, here's the example we're creating today. We've got the ChibiAkumas character. It is actually 4-color, but I've not set a proper palette, so it looks all kind of similar. But even though the sprite is 4-color, this mode is actually 16 colors. It's just the sprite only uses 4 colors because I'm using it on a lot of 4-color systems, so just for convenience there. So what commands are we going to look at today? Well, the commands all have a 4-character code, but they're quite unintelligible, and the names that they stand for aren't much more help either. So I've given a very basic description here, and that'll make it hopefully a little bit more clear to us. And we'll be using these 3 commands today. And to be honest, if you're programming the VDP, you'll probably only really need these 3 commands because these are kind of the best commands for just general use. So the first one is HMMC, which means high speed move from CPU. Now what that means is we're copying data from the normal Z80 memory into the video VDP memory. So this is how we get our tiles or our sprites from our code or our disk or whatever into the VDP memory, because the VDP memory is very fast. This command, while it's called high speed, isn't actually high speed at all. So you really only want to do this when you're getting your data ready at the start of your game, and then you copy it around the VDP memory, which is very, very fast, and that's what you do in general terms. So next we've got high speed move here. This copies one area of VDP memory to another area, and the way we use this is the screen is 256 by 192, and if we use 2 screen buffers, the second buffer would end around 512 pixels down, because the screen is a virtual screen of 256 by 1024, and that leaves the Y lines from 512 to 1024 completely unused. And what we do is we'll put our sprites in that area, and then we copy them from the hidden screens areas to the visible screen, and that's how we get our sprites on the screen very quickly, because as I said, this command is far too slow for that. This is the fastest command for doing sprite data. There is a low speed command that has the benefit of being able to do transparency, but it is much slower. Nowhere near as slow as this. It's the best way of doing transparency, but there is a significant difference. And if you look at ChibiAkumas on the MSX2, you'll notice that some of the sprites are transparent, like the ChibiAkumas sprite, and the sprites that walk along the floor. But the sprites in the middle of the screen, they aren't transparent. They have a black border around them, and that's because I'm using the slow command where I need that transparency. But where I can almost get away with it, I use the high speed command. Now on the V9K version of this, it always uses the transparency. The V9K is so fast, it really makes no difference. And I think actually there isn't a high speed command, because the low speed command, the logical one that does that transparency, is actually as fast as you could get anyway. So transparency all the way on the V9K, but on the MSX2 you do have to sacrifice the transparency if you want the speed, and it's not that fast. The MSX2 VDP, it's not going to compete with the Super Nintendo. It's decent, but it's not going to compete with Neo Geos and PC engines. So we do have to be conservative with it. We're not going to use the transparency today because we're not doing sprites, we're just doing tiles. Now the final command we're going to look at is HMMV here. Now this is another high-speed move command, and it copies from the VDP to the video memory. And what this means in effect is we are filling an entire area with a single byte. So this is basically our flood fill command. If you look at ChibiAkumas again, you'll notice some bits of the background have gradients. They're actually filled by direct memory access. Some bits have repeating mountains or something like that. They're done with this HMMM command. And then some areas are just black or a solid fill. And these are done with HMMV, because HMMV is the fastest fill command on the system. So this is our fastest, this is our second fastest. The LMMM command, the transparent one, would be next, and then HMMC is the absolute slowest. So there we go. Those are the commands we're going to be using. The registers we're going to be using are numbers 32 to 46. Now you'll notice these are basically consecutive. I say basically because some commands don't need this color one, but apart from that they are consecutive. So these are the ones we need for the commands we're looking at here. The other ones we might need for setting up our screen mode and things, but for our general day-to-day commands, these are what we need. And we probably want to start with the startx, if there is one. There is no startx for this fill command here, but if there is one, we would need to do startx. Otherwise, we just need to start with destination x, destination y, number x, number y, a color byte where appropriate, move direction, and then the command. The command has to come last, because when the command register is filled, number 46, the VDP will actually start processing. So if we haven't set this data before we run that command, we're going to make a mess. So those are our commands, those are our registers. And we do need to know about some status registers. The important one is bit 0 here. This is whether the last job is actually finished yet. So we need to check this every time before we do a job. Unfortunately, the system firmware has to, on its interrupt handler, has to check the status register, because it's the VDP that fires the interrupts. And if you don't check its status register, you don't have to do anything with it, but you have to check it. If you don't, the VDP will keep firing interrupts, and your interrupts will fire infinitely. The problem with this is that the default firmware interrupt handler doesn't set the status register before it checks it. So if we change to status register 2, when the interrupt handler fired, it would check status register 2, think it had done its job, return, and then the interrupt will fire again and again and again. So we have to disable interrupts, check status register 2, set back to status register 0, and then turn interrupts back on again for when we're checking if the VDP is busy or not. So apart from these, which we need to do our commands, there are two other registers we need to look at. Register 15 is called an indirect register. This allows us to fill the registers consecutively with an out-I command, and that's why I stated it was important to note these are all consecutive from 32 to 46, because we are going to use that indirect register. So we're going to use register 17 for our filling of these with out-I, and the other one is register 15, which is how we select our status register. So we've talked in quite general terms about what the registers are, what the status registers are, and a bit of the concept. And as I said before, I'm going to go over this fast, and I know it's probably a bit confusing for you, but the reason I'm going over it quite fast is I only want to give you an introduction, because as I've said, if you don't understand this, if you think this is silly, this is complex, I don't get it, well, just don't bother, just use my example code. It will do the job for you. It's only if my example code is too crude for you and you really want to dig into the details that you actually start to need to think about these. I want to give you an introduction to this so you'll understand it a bit and you won't be too scared of it and you won't make the mistakes I made. But as I say, I'm really recommending you just use my code, because my code is good enough for ChibiAkumas, both on the MSX2 and the V9K. I'm pretty sure it's going to do most jobs you want as a beginner. So although I'm trying to explain it to you so I don't lie to you about how it works, I don't want you to think you need to know all of this stuff to be able to do anything, because that's completely untrue. Now, if you want to get into the real details of how the MSX2 graphics chip works and really understand it all and maybe make changes to the things I'm not explaining, this is the PDF you want, the Technical Databook Programmer's Guide. Now, if you look through this, this is a long, complex document, and I don't feel it's really very simple to use, but this is mostly what I learned from, how I got to the point where I understood it enough to write my modules that call the system. So if, as I say, if you're wanting to do clever things with the screen mode I've not covered, or if my routines aren't working in the way you need them to, this is what you want to get. I'm afraid you've got to read through it until you understand it, and then you'll probably understand more than I do, so well done there. But as I say, I just wanted to make you know that was available, and I've linked it on my website. You can see just here, you can download it from there. So by all means, take this as far as you feel confident doing. If you want to learn the full details, get that PDF. If you just want the basics, just use my stock source code. If you want somewhere in between, well, here's on screen is the details of how my source code works. So anyway, we need to set these registers to be able to do anything with the VDP. So how do we do that? Well, we have to use the VDP ports as usual. The main one we're going to use is the control port, and that is to select the register. So what we need to do is we need to think, well, what register do we want to set? Well, let's suppose we're going to set register 15, which is the selection of the status register. So if we wanted to read in if the VDP is busy, we need to set register 15 to 2 to select status register 2. We do it backwards. What we do is we select the new value of the register 2. We send that to the control port, which is 99, hexadecimal 99, sorry. Next we set the number of the register, so register 15, plus 128. And in this case, 128 is a special code to tell the VDP the data you're getting now is actually selecting a register. So it's a special control code, really. It's not, it doesn't, you can't not put that in. It doesn't give any extra feature adding that. It's just sort of part of the stock code of selecting a register value. So here we've selected the new value for register 15, but if I swap that 15 for 35, then I would be setting the high byte of SY as to 2, and we can perfectly do that. That's how you set a single register, but there is a better way. As I said before, we want to set ranges of registers, and what we can do there is use this indirect register, register 17, set that to the value of the first register we want to set. So for example, if we set A to 32, outed it to 99, and then set A to 17 plus 128 and outed that to 99, then we would set the indirect register to 32. And what that would mean is that when we outed a byte to the incremental port, to port 9B, which is the incremental port, it will be written to register 32, but then the pointer will change to 33. And so when we out another byte, we will out it to 34, to 35, and so on. And this is what my code uses. It sets the incremental register to the first register we need to set, which is usually SX, and then it just pumps a series of bytes in the order that are set up in the order that the VDP needs them, and then the last byte is the command. And this allows us to control the VDP in a very, very simple way. And that's why I said, really, you don't need to worry too much about how the VDP works to get work done today. So let's have a look at how we're actually going to use the VDP then. So let's start by taking a look at the clear screen command. So this is the code that does the clear screen command, which sets all of the pixels to black. So we're going to use HMMV, which is a fast fill command, and the command we're going to be using is VDP HMMV, which we'll have a look at in a moment. So the first thing we need to do, disable interrupts, run this command to check if the VDP is ready. This command will not return until it is, and then turn interrupts back on. This command also restores the status register to 0, because as I said before, the firmware needs that. So now we can turn interrupts back on. We load HL with the address of this buffer here, and then we call VDP HMMV. Now you'll see there's some numbers here, and there's some bytes next to each of these numbers. And if you have a look, you'll notice DX36, DX36, DY38, DY38. And you see what we're doing is we're setting the incremental register to 36, and then we're using OutI within this function. We'll have a look in a moment. We are using OutI to pump all of these bytes straight into these registers, and then the last byte here is actually the command for HMMV. Now this one, as I say, we don't need to really use it, but we just put that in. And so this is the color we're doing. So this function will set this entire range to 0, 0. But if we wanted, we could just change this. So if I change this to FF, and I change this is the number of X, so it's set to 256. But if I change this to 80, and so now you can see that the left-hand side of the screen has been filled in white, which is color F, color 15, and the right-hand screen's got corruption because it's not been filled at all, and that's because of the changes we made to the code here. So you can see that just by changing this to here to 128 from 256, of course in hexadecimal, and just by changing this color number, we can really quite easily reconfigure the code to work however we want. And now it's back to normal. So as I say, these functions make it very easy to get jobs done quickly without reading the source code all the time, basically, and figuring out all of the registers. So let's just have another look at these. So DX is destination X, 2 bytes. DY destination Y, 2 bytes. NX is the number of horizontal bytes. NY is the number of vertical bytes. In this case, color is the bytes of the color we're going to fill in. So first pixel, second pixel, repeated across the screen. That's all we can do. You can't do any checkerboard effects on alternate lines. You'd have to do multiple commands for that, and that would end up so slow you wouldn't be able to do it in real time. So it's not really an option. The move command is the direction, not really relevant in this case, and that's the command, so don't change that because otherwise this won't work. So that's how we do a clear screen, but we also need to do other things. Let's have a look at actually how that clear screen command works in the source code then. So this is the command we're using today. So this is the HMMV command, and it actually can do other jobs as well, because a lot of them are very similar just depending on the number of bytes we're having to write to the VDP. So what do? Well, we select the first register we want to fill, which is number 36. Let's just double check that. 36, because the first thing we don't need a source because we're filling, so we just select the destination register 36. We then set register 17, which is the increment register. We need to add 128 because that's the rule of when we're selecting a register. Now you'll notice it says 128, no increment here. If we set this to 36 plus 128, the indirect register would always point to 36, it wouldn't increment. So you maybe want to use that in some cases so that you can use the indirect port to always point to one register and the normal port to point to another one or something, I don't know, but that's what it is. Now, so that's now selected our incremental register. We then select the port for the incremental register into C here, and then we've got a bunch of bytes here. Well, what are these bytes? Well, this is the byte code for the out-I command. So EDA3 is the equivalent of an out-I, which is out in increment. Now, why haven't I put loads of out increments? Well, it'd just be a mess. You know, right, we've got one line here that's doing the equivalent of about 8 or 9, I think it is. So it just takes up less screen space because we're not going to change it. We don't need to debug it. So let's make it nice and neat. And then here's a sort of sample command that you can use here. So if you're going to do the same command every time, then I'd suggest, just like I did here, you create a new template and pass that template here. But there's a generic one here called VDP my HMMV. So you can poke in your values here if that's more appropriate for you. You can do either. So this is the fast fill command, but we've got some others. We've got a special one here, the hyper version. This actually, if the VDP is busy, you can actually use the memory access port like we did with our previous example where we used the screen as a bitmap to write bytes to the screen while the VDP is drawing some huge sprite. And this is how ChibiAkumas does the gradients on the MSX2. The gradients are done by memory access by the Z80 while the mountains of the background and the fills of the background are being drawn. And that's how there would have been no way to get those nice gradients fast enough with the VDP commands. And the VDP commands of filling the screen and drawing the clouds and the mountains was taking too much time. There was nothing else I could do anyway, and so it became a good compromise to do that. But in this case, if all you need to do is fill the screen and your VDP is busy, this will fill the screen until the VDP is no longer busy by using the Z80, and then as soon as the VDP is ready, it will pass the remaining job by a HMMV command, which we just saw. So a bit of a tricky command there, but we're not going to use that today. So we've got HMMC. Now you'll see this says generated, and this is how we get our data from the processor and the processor memory into the VDP. So we're going to use this to define our tiles. We can't use these busy check versions because these rely on the status register 2 being selected all the time, which it is in ChibiAkumas, but because we're using the firmware here, we can't use it. So we're using that firmware safe interrupt handler. And you'll notice there's more out-I commands here. So how does this generated command work? Well, unfortunately, it's a little bit tricky. The VDP will write an area and it will fill the area with bytes. But unfortunately, we have to give it the first byte for reasons unclear here as part of the command in register 44. So this will select the area. It will define the area for us, write that first byte, and then it returns, and C will point to the indirect register. And that allows us to get our pattern data, be it sprites or in this case tiles, into the VDP's memory for fast use later. So we'll see that being used again later. And again, there's examples of all the commands here. And so when this function returns, we've got the memory pointers set up to fill the area. The first byte's been written, and the C register will point to the correct port to write the remaining bytes without commands. So that's how we get our tiles and our sprites to the screen, tiles in today's example. When it comes to drawing those tiles quickly onto the screen, we're going to use HMMM, which is the fastest sprite type command. There's also LMMM, which is a bit slower, and it can do transparency, as I said before. They both write the same number of bytes to memory, to VDP memory, so they're actually sharing the same code here because they are identical. The only difference is the command, which is of course passed in our data array here, or here. You'll notice it's different. But in both cases, we need a source. That's wrong, that should be SX. We need a source X, a source Y, destination X, destination Y, a number of X, a number of Y. We don't need a color, it's just there for completeness because we need to write the same number of bytes. The move is the same as always, doesn't really matter in the case of this command. And then the special command code which tells it what actual job to do with the data. And remember, this has to copy from an area of the screen that we've defined our tile or our sprite in, off the screen presumably, onto the visible screen. Now we've got our VDP safe wait here, which is the one we'll be using today. All it does is it uses the generic wait command here, which loads in register 2, checks if it's busy by popping the rightmost bit off. If the rightmost bit is 1, then we loop around here until we're done. And then once we get back here, we reset the firmware register to 0 using this XOR here. And then we set that in, and that selects the firmware's register, so the firmware will be happy again. And after we've run that, we can turn interrupts back on. We've got some initialization routines here, which set up all the defaults. I'm not going to go into those, partially because I don't understand some of them, I'll be honest with you. All I can say is they do work. So that's the basics of what we're going to be doing today. We've got the VDP set read address, set write address, which we've looked at before in the bitmap lesson. And we do have some palette functions, which we are going to have a look at in a later lesson as well. This, as I said, this is copied basically straight off ChibiAkumas. So there's a lot of functions in here we're not going to cover today. But, you know, you're getting everything here. So hopefully you can create something pretty good with it. So let's have a look at the actual code that does the work. Because that's how we directly interface with the hardware. But we actually need to look at the code that does the jobs of getting the data on the screen. So as always, the my sprite editor can export. It's not the save raw bitmap in the MSX option, which is the normal MSX2 in the sense of the bitmap tutorials. You need this raw VDP tile bitmap. The organization is different. It splits the image, the Chibico sprite in this case, into 8x8 chunks, outputs each 8 lines of the first tile, then moves along. So instead of going like this, it goes kind of like this in a zigzag across each 8 pixel tall line, and then carries on with the next one. But as I say, just if you just want to get started, just use my exporter and that should do you. So we're going to have a look at how to define tiles then. So let's have a look at that. So here's the define tiles function. So the way we're going to use the MSX1 VDP is like this. Now the screen is 256 pixels wide, and it's not possible to have hidden screen space on the right hand side of the screen. The screen's 1024 pixels tall, even though only 192 are visible, but there's no spare hidden screen across the right hand side. So what we're going to do is we're going to start our tiles 512 pixels down, way out of the way if we were having 2 screen buffers, each 192 pixels tall. If there are 2 screen buffers, the second one actually starts at 256. So there is a small gap in between the 192nd pixel, which is the last line visible of the first buffer, and the start of the second one at 256. And my ChibiAkumas game actually has the character sprites and a few other sprites hidden in that area, because I really had to use everything available to me. So when it comes to defining the tiles, we're starting 512 down. Each tile is 8x8 pixels in this code, and the screen is 256 pixels wide. That means we're going to have 32 tiles on each line. We're specifying a tile number, so by selecting the 5 rightmost bits, we can work out by multiplying by 8 the X position of the tile we want to write to, because we're defining in this case, and then we just store that into the X position, and then we take the remaining 3 bits, multiply them by 8 again, and we store that in the Y position, and that works because we've already set the 512 start with this 2 here. So then we just have to check if the VDP is busy. This will return when it's not. Then we load in the address of this buffer that we've just defined here, and we've just filled in with the correct values here. You'll notice it's already preloaded with 8x8 as the size of the tile. And then we call this, which defines the first pixel, which you'll see we loaded in here because we have to load in the first pixel. I know it's really annoying, but you have to load in the first pixel into this on the MSX2. The V9K you don't, but the code I've written actually emulates it in the same way. So you can use it. You can use this exact code on the V9K as well. We call the command here. We then get back here, and we are now ready to send the remaining bytes of our tile definition to the VDP. And because the VDP has been told we're filling an 8x8 grid, we don't need to do any relocation of the writing cursor when we get to the end of a line. So what we do now is we send our byte data, and we keep filling that data in until we get to the end of a tile, because we're allowing us to define all of the tiles in one go here. So when we get to the end of a tile, we have to start the next one, and so we jump up here and we loop through again. And so this will define all of the tiles in the same way as we did for the other systems. So we just load HL with the address of the tile memory, DE with the tile number, or E with the tile number more specifically, because this only supports 256 tiles, because our most basic systems like the MSX1 only support 256 tiles, so it didn't seem worth supporting more. And BC is the byte count of the data buffer. And we're accessing the port here to write the data to with this VDP send byte data definition here, but it's actually the same address as the indirect port anyway, which is 9B, which you can see here, they're both 9B. So if we weren't using BC here, we could have actually used C as it was returned here, so we could have done out C, A. But in this case, because we're using BC as a counter, we can't do that. So that's how we do our color tiles. There's a very similar piece of code here to do black and white tiles. Very long and annoying because this is converting our 2-color font, black and white font, into 16 colors for the VDP. But basically it's the same code, just with a load of bit shifting to convert 2 colors to 16. Now when it comes to actually getting a tile on the screen, the procedure is basically reversed. So we're now using my HMMM, which is the fast copy routine. Again, we're working on an 8x8 tile. Again, we're starting from 512 pixels down where our tile definitions are. And so all we're doing is basically reversing the procedure. So we work out our x coordinate by taking in L and taking the 5 rightmost bits, which will get a number from 0 to 32. We multiply that by 8, and that is the start x position of our tile. We take the 3 remaining bits, we multiply them by 8 as well, and that will get us the Y line of the tile that we want to select. We load those into start X and start Y. We then load in the destination, multiplying by 8 again. The destination is an zero-based XY coordinate in DE. We shift them left 3 times, which effectively multiplies them by 8. Store them in the direct destination X and Y. Number X and Y are both set to 8, as I said. And then all we do is we wait to check the VDP is not still busy. We load in our definition, my HMMM, and we call this function, and that will do everything for us. And so now the tile we selected is in the location we selected it. And that's really all there is to it today. As I've said before, if you use these my HMMC and HMMV and what have you type functions, it makes everything very, very straightforward when it comes to actually getting stuff to the screen. So, I mean, the final part of the equation, I suppose, is the fill area with tiles command. It's basically the same as every other time. If you've not seen the previous lessons, because we're working in 8x8 tiles, when we want to show that Chibico character that is 48 by 48, the way we're doing it is we're filling a grid with consecutive tile numbers and then defining that those consecutive tiles to be the chunks of that Chibico character. And this is why I said here, this save raw VDP tile bitmap is splitting the Chibico into 8x8 chunks, exporting them in the correct order for this function here, and then so just by filling this area with consecutively numbered tiles, that's how we get our Chibico character to the screen. And that's all that this does. It's just consecutively using this copy tile to screen command to copy those numbered tiles into a grid, and that's how we get our Chibico on the screen. But there is another trick we can do. As I said, this code will work exactly the same for the V9K. So if I unrem this option here, V9K, what happens is instead of the function we've looked at today, this module is no longer loaded, and this alternative version is loaded. And you'll actually see that all of the commands exist in virtually the same structure. They are slightly different. The command codes are different. There's some other tricks going on, and this one isn't as well code commented because I specially code commented this version for today's lesson. This version's a bit raw straight out of the ChibiAkumas code, but it does work, and I can prove that to you right now. So here we go. Now you're probably wondering, well, why is the Chibico sprite white? Well, that's quite simply because I've not defined any palette, and so we're using the default palette, and the V9K's default is the first colour black, everything else white. So there we go. But the point I'm making is that the code completely unaltered works on both systems, and later we will look at palette code that again abstracts the fact that the V9K requires different palette information to the MSX2 and allows us to define our palette in the same way for both systems, again coming straight out of the ChibiAkumas code. So there we go. We've not only programmed for the MSX2 today, we've programmed for the V9K, and we've done it all in the same amount of time. So I hope you've enjoyed today's lesson. It's been a bit fast, I apologise for that. I didn't want to go into huge amounts of detail on this because it's kind of one of these things where you'll either understand it or you won't, and I'll probably do more lessons on this in the future anyway. And as I've said before, if you really want to understand it, get that PDF and dig into it as much as you dare. But you know, what I've shown you today should tide you over for the basic stuff. All of the stuff you're seeing today is available for download, and the ChibiAkumas MSX version will be coming out soon. So, and that'll be open source as well, so you can even use the source to that. I totally encourage people to use all of my code in any way they want. As well as that, Grime Z80 is also out. That also supports the MSX2 and the V9K, and that's actually what this code was written for that you've seen today, the Tilemap code. So check out the Grime Z80 project, download that, have a play with that. And then the other thing is, if you're a CPC user, what we've looked at today, this concept of registers and that V9K code, with relatively little modification, this V9K module should work for the Amstrad CPC. I've actually got a test version that in theory would work. The only problem is I don't have the hardware to test it, and there's no emulators that support it yet. So as soon as I get a way of testing it, I will check that works, and I will make sure the Grime Z80 does work for this Amstrad CPC with the V9K, because it's something I want to look at even if no one else does. So again, thanks for watching today. Next week we're going to have a look at joystick controls on the Game Boy, the Master System and the Game Gear. But please don't think we're done with the MSX or anything. That couldn't be further from the truth. We're still going to look at colours on all of these systems. Absolutely all of them. We've not done palettes yet, and we're going to have a look at sound on all of the systems as well. So we're going to come back to the MSX. I'd just like to move around the systems a little bit, keep all the viewers happy depending on which systems they're interested in. But I think this has been a really good lesson for the MSX people today. So thanks again for watching, and goodbye.